Again, good morning and welcome to week 7. Week 7 is actually, we have a major thing going on this week that I really want to bring your attention to, and that is the review for the exam. It's already on Canvas. Some of you already took it. The plan is similar to basically the review for exam 1, namely the fact that it's going to be graded. The review is going to be graded as participation, meaning that if you take it, regardless of how much you score in it, you're going to get full credit for it. And of course, that goes towards your participation. So I strongly urge you to do it for two reasons. First of all, it prepares you for the exam. And second, because it's for credit. So you're strongly urged to do it and do that before it's over, because I think on Monday, I don't remember exactly what time. Usually my deadlines are noon, are 11 p.m. Because there is an exam coming at night. So I think the deadline for this one is before that. Okay. So it's not going to be at 11 p.m. So the review is going to end before that, and to give you time to basically breathe from that and actually be ready for the actual exam. The actual exam is actually a little different also this time around. In a sense, you will have a lot of time to finish the exam. It's going to open up in the evening of the 12th and be open for you guys until 10 o'clock in the morning on Tuesday. So if you're working during daytime, you can still do the exam at night. If you are working during nighttime or you want to sleep or watch TV or whatever you want to do, you still can do it during the allotted time. So you can still wake up in the morning, come 8:30 in the morning, take the exam, and you're done with it. Okay. You need to know though that this exam has an hour and 35 minutes to complete. So you need to make sure you start at least at 8:25 if you want, at 8:25 on Tuesday morning, that is, to complete the exam by 10 a.m. Okay, and to use all of your time. There will be no exceptions to that. By 10 a.m. on Tuesday, the 13th, the exam will close and I will not take anything after that. So please take that in mind, keep that in mind. So if you plan to use all of your 1 hour and 35 minutes and you decide to take it on Tuesday, the latest you can start on it is 8:25 in the morning, just 5 minutes before we normally start. It has 55 questions, the actual exam itself. So that's why I'm factoring in that, the fact that you take your time to do the actual exam and also you review the exam. There is a built-in a lot of time for you guys to go through it to make sure that the question that was bugging you, look at it again and think about it before you submitting it. So that's the two things that are slightly different this time around, in a sense that the review does not end at 11 p.m. on the day before of the exam, but rather it opens before. And that is the reason why is because the actual exam starts at night, okay, the night before. So at 10 p.m. actually on the 12th. The other thing also in terms of assignments, other than the discussions, which are usually now routine for you guys, basically that's something expected. There is no assignment. There are no quizzes this week. There are no homework, no nothing other than the discussions after the classes. That is again to keep you focused on the exam and hopefully do the review, and then you're ready for it and you do the exam. However, there is a quiz for this week, but it's not going to be done this week. It's going to be ready next week after the actual exam. So in other words, we still have to be held accountable for chapters 12 and 13 of this week, in a sense that we have to make sure that we also know the content for them through quizzes. So that's basically in a nutshell how this week is organized with the next week. And another word of caution also, in terms of the exam, you may discover that there is an issue. Sometimes things pop up, okay? There's something probably not clear in the instructions, or question that is probably something is off about it or something, and you discover that. Uh, you have to let me know immediately. I will open a discussion, and actually, I will create a discussion for the exam dedicated just for the exam. I strongly urge you to subscribe to that discussion, meaning if there is an update on that discussion because of a problem in the instructions or a problem in the okay, no problem, Sherry. Anyway, I mean, I wanted to really hopefully make it useful for you guys too. That's why I reduced the number a little bit too, because you guys, I want you to really take advantage of that. Anyway, the point is that I was trying to say in here is that if you discover a flaw in there and the discussion, you need to subscribe to the discussion so that if there is an update to the discussion, you need to be aware of it. In other words, you receive notification from Canvas that an addition was added to the discussion, and probably you're going to go and look at it. Now, I cannot answer any replies, and there is a deadline for it at least half an hour before the exam is over because there will be not enough time for the notification to go from Canvas to rest of you guys saying that there is a change. So if there is something flawed in the exam, a problem, for example, and it's within half an hour by the end of the exam, that's it. We have to live with that. Okay. So that's basically what I'm trying to say here. So please at least try to take the exam as soon as possible. You discover there is an issue, please let me know as soon as possible about it. And then that also avoids another problem, and that is okay, right? You're in the middle of the exam and the power shut off, or the internet goes down, or something happens, okay? Or there is, I don't know, pop up so that you're prevented from finishing your exam. Canvas will take probably what you did and that's it and submit it on your behalf. And then you have a problem because you didn't do the whole exam. But if you do that ahead of time, you still have time for you to take care of this problem later on if in case there is a justifiable reason for you to take the exam again. There is only one shot at this exam. It's not like two attempts or anything like that. So that's basically in a nutshell what these things are. So I think we talked enough about the business in hand, and we should be able to get into chapters 12, which is not part of this exam, but it's going to be part of exam 3, which is coming in about how many? 3 weeks. So that's also coming toward the beginning of November. That's actually a month from now, but that's also something that we have to start thinking ahead of for. So that's something that we have to be prepared for, and that's the whole thing is about chemistry for that chapter. Do you guys have any question? No? So we can start then today's class, which is all about basically the atomic structure and the periodic table and elements of chemistry and things like that. Oops, what did I share? Oops, no, that's not what I wanted to share. Sorry. This is what I wanted to share. Okay, so we're doing chapter 12 now. And chapter 12 is all, like I said, about the atomic structure and the periodic table. Okay. There is kind of limit in there between physics and chemistry, structure, and all of that. And it's really sometimes these things is just more of a artificial boundaries that are not really. It's for basically what job descriptions, but in real life the two have they overlap basically. They touch on upon one another. Okay, so we're going to talk about the atoms and the fact that the atoms as we know them today, all of the atoms that we have them on Earth, they're ancient. They have basically been created a long, long, long time ago. Okay. And with the exception of hydrogen, actually. Okay, what is my drawing tool in here? Hydrogen, and I mean the hydrogen atom. Oh, there are too many bars in here. Okay. And to some extent, helium. Not to some extent, to a lot of extent. Most of the helium that we see today is actually made also early on. My screen is kind of lagging. I don't know. There's something that is. What can I stop? This one in here. Let me close that. We close all of this. Yeah. For some reason, I think my computer is a little bit. Anyway, hydrogen was created in the so-called Big Bang. Okay, and helium also was created for the most part in the Big Bang. Nothing else was created in the Big Bang. Everything else was created later on by inside the stars. Okay, any other element, lithium and anything above that, was created in the stars. Okay, so the star goes through its normal process, normal life, basically combining hydrogen atoms early on in the core and creating other elements, which is mainly helium in this case, and to sometimes lithium also. Okay, lithium is created later on and toward the end of the life of the star, and then toward the end of its life, now the helium actually starts to combine, making other elements, and because it goes through a very very rapid process, basically creating heavier and heavier elements up to iron. Okay, you will see the iron in the periodic table is not really in the middle of the periodic table, but it's toward the beginning. Once the star starts to make the iron, at that point the star is done through. It's dead. It's going to die. It's going to collapse. Actually, the once the star starts making iron, it has signed its own death. Okay. Not all stars do that too, though. Not all stars get to that stage. You have to have a big star to reach the point where it starts making iron. Some stars, like the sun, for example, will not reach that stage, will not be able to create the iron as we know it. Okay. But the point being in here, at that point, is going to go supernova. It's going to collapse on itself once it reaches that point, creating heavier and heavier elements, the rest of the elements that we know, basically in the periodic table. There are 115 elements that we know can exist in nature. Only 90 of them exist. Okay, the rest were created in the laboratory. Okay, so that's basically how the rest of the 90 elements, basically most of them, they are created during the supernova stage, which is an indication that the fact that we are here on Earth, when we have a lot of heavier elements, that we must have been created a long, long time ago too. Everything that we have in here right now must have been created in a supernova. So the point in here is that atoms, they are ancient, they are very old, they have been created a long, long time ago. Okay, so that's the point in here. Also, we're going to be talking about elements and the difference between an element and an atom, and they're interconnected. Sometimes they're used exchangeably. Okay, when we say an atom, we mean an element, and vice versa. Basically, an element is any substance that is made up of a single type of an atom. Okay, so that's why they're used exchangeably. Okay, so the number of elements is the same number of different atoms, if you wish. Okay, then we'll talk about the structure of the atom itself, which is made up of two kinds of major structures. First of all, there is a nucleus, and there is the electronic cloud. And then inside the nucleus, there are so-called nucleons. The nucleons are basically two types of particles. They are the protons and then the neutrons combined together. The electrons, which form the electronic cloud, they sit outside of the nucleus. This whole thing represents the atom, and it's a model, really. Atoms were classified, or elements were classified, in the so-called periodic table by Mendeleev initially. Okay, in a specific structure, you have groups. Okay, depending on how many electrons in the outer shell, basically, and then you have periods. Okay, different masses as you move along. Okay, so that is basically what the periodic table in here is. So that's the words in here that we will be looking at, namely the rows are periods, the columns are groups. Okay, and there is a structure, there is definite structure for that. Again, we'll try to understand that. We're not required to memorize where each and every one of those elements are, what are they called. But the thing with it is, when we see a periodic table, we should be able to understand some chemical and physical properties based on the location of the element in the periodic table. Again, we're going to talk about an idea in here, the whole thing that I described earlier for the atom, namely the fact that you have a nucleus and you have an electronic cloud. That's a model. Okay, that's a representation. There are two kinds of ways of looking at that. There is a physical model, which is a real representation of the atom. Okay, and there is a conceptual model. Conceptual model focuses on specific properties or specific roles. In this case, it's probably a little easier to see that, but don't confuse that with the actual thing. Okay, it's just a model. It's just a representation, if you wish, of the properties that you have in hand. So if we're talking about energy, for example, we're going to probably represent the atom with different energy levels. Okay, 1, 2, and so on and so forth. So we have different energy levels for the atom. If we're talking about, for example, about the how the orbits would look, probably we'll have different representation and so on and so forth. Okay. And like the solar system, for example, when we represent it by an ellipse, where the sun is in one of the focal points, and the planets are revolving around it in specific patterns, that is actually how the actual thing looks like. That is actually, if we look at it, if we were to fly away at least, and probably be far away from it and try to pinpoint where those things are, we will see them actually orbiting that one. So for the solar system, that is actually an exact representation, especially if we draw it to scale. That is actually a representation of the solar system. For this one in here, again, depending on specific rules, because at times it's a little bit hard for us to even understand the reality of it. Because one of the things we will see, for example, in here, is the duality of elementary particles. For example, is the electron a particle or is it a wave? And at some point it behaves like a wave, so we have to represent it like a wave in our models. And sometimes it actually behaves like a particle, so we have to represent it with a dot, okay, and start to track it. So which one it is depends basically on the actual experiment. Depends actually on how the electron is basically. So the actual electron is both this one and that one, which is kind of confusing for us at this level because we don't really cannot imagine it because we don't live in that universe. We don't live on that scale. So again, we're going to talk about this idea of models and how to represent things. We're going to also talk about spectroscopy, and spectroscopy is a very important branch of basically science, where you're going to every element, every compound, as a matter of fact, every molecule, if you wish, has its own signature. Let's focus on the elements. Every single element has its own signature. It has its own spectral lines. For example, hydrogen has, let's say for example, this lines separated by specific distances and specific frequencies, okay, on the spectrum. For us, for hydrogen, for specific energy levels, they actually look different colors. Some of them look red. One of these lines, for example, let's say, for example, this is red. This would be blue, and the other two colors are somewhere in between them. Now, if I happen to do a spectral analysis for substance that I don't know what it is, okay, and among other things, I see these 4 lines lined up in these specific locations on the spectrum, then I can assert without a doubt that hydrogen is existent in that structure, whatever it is that I'm trying to analyze. So I know for sure that it exists there. Okay. So for example, none of us has been to the stars. None of us has gone to even to the sun, let alone to the next star, or any other star for that matter, or galaxies that are millions of miles away, probably billions of millions of miles, millions of light years away, probably billions of light years away from us. Okay. But we can assert with confidence that this star has this much hydrogen in it, and this star has this much hydrogen in it, and this star has probably this much helium in it, which is probably more important, and this star has this much helium in it, and this star has actually these traces of lithium in it, and this one does not. So this one must be newer generation star, and this one must be an older generation star. I can determine the age of these things when the stars were determined. This star, for example, just because of doing spectral analysis, just because I can just look at the light that is coming from that star and basically break it down into its components and find how much stuff is in it. Okay, planets revolving around it, and the planet is hit by the radiation from the star, and the planet probably radiate back. So if I were to do a spectral analysis, I can also determine the structure of that planet and see if it has oxygen on its surface or not. And if it has oxygen, then it implies that it has life on it. So there are a lot of exciting things. Not only that, for example, for practical aspect in here, criminology, they want to know, for example, what did this person had for lunch yesterday? So they go and analyze basically what is in his stomach after he passed away. Of course, we're talking about a crime here. Uh, and they can determine what did he have for lunch or what did she have for lunch. Actually, they can actually physically open that and see, but at least some other things, for example, that are very hard to see, like, for example, traces of arsenic in the bloodstream or whatever that is, they can find it using spectroscopy. They can do that and they will find exactly how much that person had, is it deadly levels or not, or whatever that is. So that's again using spectroscopy. You have a lot of applications in science, of course, to determine structures, to determine astronomy, to determine and other applications too. So again, every single element has a signature. There are two types of spectral analysis that you can do. There is a so-called emission spectrum, and there is an absorption spectrum. Emission spectrum is when a substance emits light, and we will see this specific frequencies existing for a specific element, then we know it exists there. Absorption spectrum is the other way around, actually. You shine light from a source, all everything else passes through with the exception of few lines that are absorbed by the atom in there, by the atoms or the elements that exist in that substance. So my spectrum on the other side will be missing some frequencies. So I will have back recovered all the spectrum with the exception of these lines. So that is actually an absorption spectrum. Either way, I'm analyzing basically the existence or the lack thereof of a specific atom or specific element, okay, in the structure that I'm looking for. Either one of them tells me whether or not I have that substance in there or not. So that's basically what this thing is. Then we will have actually after that, we will talk about the quantum hypothesis. And the quantum hypothesis, we're getting really to the right approach to how we treat the atom, namely quantum mechanics, and the fact that the energy or the light itself is actually quantized. And from there, we'll build some ideas to give us a clearer, basically, model of the actual atom. And that is the shell model, which is really a better model to explain the periodic table, among other things, and everything else you see in terms of the elements. Actually, if you do an experiment today, this model will be the best in explaining the results that you have in there than the other previous models. Again, we're trying to make it give an image, put an image in our heads on how this atom looks like. Okay, so that's basically in a nutshell what this chapter is about. So, and we spent what 23 minutes on it. So I think we're done. No, I think let's get into a little bit of details in here. Okay, I said already that atoms, uh, origin of most atoms goes back to the birth of the universe. The exceptions I say in here is for hydrogen and helium. Okay, hydrogen and helium. That is the discussion point in today. Okay, what are the exceptions? Ancient. Oh, here it says elementary. Elements heavier than hydrogen and much of the helium are produced in the interior of stars, okay? So during the Big Bang, these are the two elements that formed, okay? Hydrogen, I mean, helium also still forms in the stars because right now in the core of every star, including the sun, on a regular basis, helium is being formed all the time, okay? So that's the reason why helium is a transition between the two. So if you look at the periodic table, you will find hydrogen on one side and everybody and helium on the other. Scratch the helium for a second. Everybody else, with the exception of hydrogen, was formed later on in the stars, and it's still being formed as we're speaking right now. Okay, still manufactured in the stars. So when Carl Sagan says that we are star stuff, he really meant it. Okay, we are made out of star stuff, all of us. Okay, everything, as a matter of fact, that we see before us, with the exception of hydrogen. Okay, that was made before the stars. Okay, so everything was made by the stars, including us. Okay, with the exception of these two elements. That's your discussion thing. Okay, got it? You guys can put it in your own words. That's in honor of Mr. Carl Sagan. If you have never heard of him, it's a really good thing also to look him up. Okay, Carl Sagan. What is my sharing thing in here? Share. Okay, this is a funny question in here. Okay, which of the following are incorrect statements of the atoms? Atoms have been made around since the beginning of the universe. Atoms are mostly empty space, which is true. Okay, in a famous experiment by Rutherford, he basically had gold sheets. Okay, and he shone a alpha particles, which is actually helium with no electrons, through them. So they are positively charged, and he noticed that for the most part, they went through unimpeded. Supposedly, if they're supposed to hit charged particles, like the nucleus, they're supposed to be repelled or deviated or anything. And he found some that actually went back, and some of them actually deviated from their original path. But for the most part, all of the alpha particles went through unimpeded, meaning that there is the atom itself is empty space. So that is actually an experimental fact from the early on when this subject was being investigated. So that's basically the Sarah, probably sometimes these questions are confusing. Okay, let me tell you why it's not A. Basically, the question is incorrect. So it's asking for the incorrect, not the correct. So we're looking for the one that is not correct and say that is the correct answer. So sometimes these questions are confusing. So you really have to pay attention to. Okay. So okay. No, actually, they're intended that way. So it's not your fault or anything like that. These questions sometimes they're off in a sense that it's asking for the one that is incorrect, and that becomes the correct answer. So the incorrect answer in this case is D, which is the correct answer for this question. It's like an oxymoron. It's like a flip-flop of things. Okay. So before you answer something, try to read the question again, because sometimes it's asking probably for the opposite of what you're thinking. So again, atoms are made out of empty space. Okay. That is basically an experiment, a famous experiment by Mr. Rutherford. And then after that, it's proven everywhere that the atoms are actually, as a matter of fact, the distance between the nucleus and the atomic cloud on that scale is much, much larger than the distance from the Earth to the Sun. You think that the distance from the Earth to the Sun is an empty space? That is nothing. Relatively speaking, of course, I'm talking about sizes in here of the nucleus and the electron, for example, for the hydrogen atom, and that of the Sun and the Earth. That distance is a huge empty space. As a matter of fact, the alpha particle that Mr. Rutherford has shone through it, by the time it interacts with the nucleus, by the time it gets very close from it, the electron is very, very far away, 10,000 times or more further away. It has long time ago passed through the electron cloud, and now it's approaching the nucleus. At that point, if it came at the right angle, it's going to bounce back, or it's going to deviate, or for the most part, it's going to go straight through as if it doesn't exist at all, because it's further away from it. Okay. That was actually one of the questions from my other physics classes, one of the physics 4B, which I'm teaching right now. They had it actually in an exam 1. They were supposed to calculate the the nearest distance when the alpha particle comes in and hits actually not a gold. We did it for the exams has a bunch of elements because my exams are different for every one of you guys. By the way, that's also true for you guys too. Every one of you will have a different exam, so you may have different questions than the other people. So you might if your question, for example, is answered on the discussion, other people probably say, "What is he or what is she talking about?" I have no idea what this point is. So if that's the case for you, ignore it because your exam is probably different than the other person. Same thing. The point I was trying to say in here is that they were calculating an incoming particle, alpha particle, at different distances. Each one of them has different question, and some of them having interaction, some of them did not, and the element even itself changes from lead to other elements, zinc, whatever the person ended up with that question is, which is different calculation, different results. But the point in here is, again, it's mainly empty space for this one in here. So that part B is correct, okay? And atoms are perpetually moving, okay? If they stop from motion, whether, first of all, as the entire atom itself, or the actual electron going around it, at that point there will be completely unstable element. As a matter of fact, you have to lower the temperature how much? 0 Kelvin? It's impossible to reach 0 Kelvin. First of all, practically, it's impossible. That is actually a theoretical limit. And even at that level, even when you are at 0 Kelvin, the atoms don't stop. Because, yes, the thermal energy stops. Yes, there is no heat associated with motion at that point. There is no temperature associated with it at that point because temperature is 0 Kelvin at that point. But at that point, the quantum effect will take over and will keep the atom still moving. So A is a correct statement, B is a correct statement, C is a correct statement, D, of course, is nonsense. Atoms are manufactured in plants and in humans during pregnancy. That is actually a funny thing. If you are into literature and you read books, there is a book that I recommend for you guys to read. I enjoyed it very much. Hopefully, you will too. By Robert. I don't know if I spell his name correctly or not. Robert. Come on. That's not the problem. The problem is his last name. Heinlein. And there is a lag in here. Okay, probably I should type his name in the discussion thing in there. Yeah, I think that's how he spells his name. And the book is All You Zombies. It's a very short book, actually. It's about, I think, short stories, I should say. He's got a lot of them, and they're all fun, as a matter of fact. And this one is called All You Zombies. The reason why I thought about this one is that atoms are made up in this nonsense stuff. All You Zombies, the title. Not really a zombie movie like The Walking Dead or anything like that, but it's about this girl who happened to be her own basically boyfriend at the end. She ended up being basically befriending herself and then giving birth to herself and then becoming actually her grandmother and her grandfather, since she's the one who basically befriended herself, and she's becoming actually her own granddaughter too, and her own you can't think of it. The entire universe basically revolves around her. She is her own grandfather, great grandfather, her own father, her own basically mother, her own grandmother, her own great great grandmother, her own daughter, her own great daughter, her own great great daughter, and basically she becomes an entire universe revolving around that. And that is a problem because one of the things that could be a problem in there, and that is the conservation of matter. So where is all of these things are coming from? As a matter of fact, the title of the book, all of your zombies, or All You Zombies, or something like this one. It's a fun story actually. They made a movie out of it, I think in the year 2016 or something. And the movie's title was, I forgot what the title of the movie was, but it's not as fun as reading the book, or reading the story, I should say. Anyone read it in here? I'm typing the title in here. No? You will enjoy it. At least I did. I don't want to give up the other than the fact that the girl herself end up to being everything, entire universe, and that violates conservation of matter as a matter of fact. Okay. Oh yes, that's the title of the movie, Rudy. Thank you. Predestination. That's the title of the movie. It's not as fun as the actual book, though. Okay. For one thing, the movie was tamed in terms of the language that it was in it. And also, the girl in the movie looks a lot prettier than what the Robert Heinlein had in mind. Okay. So, so hopefully you go around read the book or read the story. It's a very short story. Okay. So elements, don't do it before the exam though. Do it after the exam. Don't read the story now and be distracted with it. So elements, a material made of only one kind of atom, pure gold, for example. If it's pure 100%, that is actually an element. A pure iron, for example, if it exists, then also that's an element. With a pure copper also, that's an element made out of the element, the atom of copper, and so on and so forth. So those are examples of pure elements that you can think of. So the atom is a fundamental unit. That is the difference between the two. So the atom is actually, the mass of the atom is of the very, very small, of the order of 10 to the negative 27 kilograms, probably 10 to the negative 26 kilogram for heavier atoms. But it's still very small thing. But the element and the atom, sometimes they're used exchangeably. And the element is actually an amount, a material quantity of it. So usually it has a finite size, like a kilogram, for example. So it's really semantic for me. I really don't care, honestly. But you have to really keep that in mind, that the element itself is a substance and the atom itself a representation of the atom. But that's basically the representation, I'm sorry, of the element. So again, I mentioned the fact that there are only 90 elements found, or 90 atoms of that specific this elements that are found in nature. Okay. The rest are synthesized. The rest are made in the laboratory. Again, as I mentioned before, protons and neutrons, they form the nucleus of the atom. Okay. And protons, they are 1,800 times, almost 2,000 times heavier or more massive than the electron, I should say. Okay. They have more mass. Okay. So if I'm looking at the mass of the atom, most of the mass of the atom will be in the nucleus, not only because of the fact that the protons are that heavy, but also because of the presence of the neutrons, which are also as massive as protons. They're slightly more massive, as a matter of fact. Okay. And now imagine the helium atom, for example. For the hydrogen atom, the nucleus is 1,800 times bigger than the electron because there is only one proton and one neutron, and one electron. But for the helium atom, it has two protons and two neutrons, at least the stable version of the helium atom. So it has four nucleons and it has two electrons. So you have 4 times 1,800 divided by 2. So it's still super massive because of the fact that you have more neutrons in here. So the mass, for the most part, exists in the nucleus. Just like the solar system, the mass of the entire solar system exists in the sun. So if somebody was to weigh all of the other planets, they amount to less than about 1% or less for the entire everything other than just the sun. The sun dominates the solar system. This is, if you wish, an analogy in that, okay? One of the amazing facts about electrons is they are identical everywhere they form. And that's true also for the protons, as a matter of fact. So if you take an electron that has formed in the lab, that we just made it, for example, from nuclear reaction or whatever that we do, or nuclear reactor or whatever that can be, and you take an electron or a proton that forms on the other edges of the universe on another star that is billions of light years away, they are the same thing. The same mass, the same charge, the same everything. Okay, so that's one of the things that is unique to these elementary particles, okay? Obviously, if you tell me that another electron has formed somewhere else with a different mass, probably you say, okay, you're going to change the name for it and you solve the problem. That's not necessarily the case. I mean, the thing with it is that these properties are identical in every which way. The electrical properties, the physical properties of electrons, and the same thing is actually for protons. Similar charges will always repel. Okay, unlike charges. So if I have this charge and this charge, then in this case they will attract. Okay, so that's basically the some of the properties of this. How this is because of the electrostatic forces. Okay. And that's critical because that tells you how these atoms form. It's because of these electrostatic forces to begin with, okay? But then you ask, what's going on in the nucleus? The nucleus has different forces acting on it, other than the electrostatic force. So you're saying, okay, the electron is negatively charged, the proton is positively charged, and they're attracting one another. So why would they stop at that point? That's a problem that we didn't understand at the beginning, but now we have a perfect justification for it. So technically, they should collapse on themselves, but they don't. And then the other problem is actually inside the nucleus, you have two protons in the case of the helium atom, where the two protons are next to one another. The neutrons, they have no charge. They are electrically neutral. They don't have a charge. They don't repel or attract or do anything. The protons are sitting to one next to one another, and they should really separate from one another and go in different directions, but they don't. That is because at that level, at those distances, there are other forces, and namely the nuclear forces will take over and will actually glue the electrons together. And the neutrons, they don't do electricity, but they do nuclear forces. Actually, they help cement the nucleus more and more. Okay? They have to keep everything stable. So that's basically how these things are. Now, technically, we have the atomic number. The atomic number is just the number of protons in the atom. Okay. If the atom is neutral, it's also the number of the electrons. Okay. If the atom is ionized, then the number of electrons could be more. If the atom is negatively ionized, if the atom is positively ionized, then the number of electrons is actually less than the atomic number. Okay. But if the atom is neutral, then the number of protons and the number of electrons, they're the same to begin with, and they're also the atomic number. Now, neutrons, they add to the mass of the entire atom, okay? And they are called the nucleons. So I just mentioned, I think briefly earlier about the helium and other elements. They come up in isotopes, and an isotope in this case is you have the same number of electrons. I mean, same number of electrons, yes, if they are neutral. The same number of protons, actually. But now, since you can have, because the chemical properties, they have to do with the electrons. Actually, even the physical property have to do with the electrons. So in this case, since they have the same number of protons, they have the same chemistry, okay? Because they can do both, participate with the same number of electrons outside. But now I can put as many neutrons as I need. So the number of neutrons can be 2 in this case, or 3, and then chemically it's the same thing, but the mass is different now. Now the atom is heavier, okay? So in isotopes, they have the same number of protons. Two isotopes have the same number of protons, but they have different neutrons, okay? Some of them are more stable than others, and that's why some isotopes, they're listed there as the stable isotopes. Others, they have a half-life, and we'll talk about that later on, where they actually decay and they go back to the stable configuration, or they actually change completely to a different element, okay? So that's basically what the difference between the two, okay? So for example, I'm looking in here at helium with an atomic mass of 5, or a helium, which is another thing in here, the atomic mass. The atomic mass is the sum basically of how many protons and how many neutrons. That's basically what the atomic mass is. Okay. It's the atomic mass unit. That's what I'm talking about in here. That is basically the number of these two and added together. But in terms of the mass itself, of course, you have to have this mass plus this mass plus this mass. And the electrons, I said, their masses are negligible compared to the protons and neutrons. So it's mainly the masses of either one of this plus the mass of this one, okay, and added together. The mass of the electron, the mass of the proton or that of the neutron is almost this number, 1.6 times 10 to the negative 27. So add all of these numbers and multiply them by that number, and you actually will have the actual mass of the actual atom. So isotopes, they have different masses. They have different physical properties. One weighs more than the other, okay? But chemically, since they have the same protons, the same number of electrons also, so they have the same chemistry. So that's the difference between them, which is the other point in here. Isotopes, okay, have same chemistry. Is it lagging also before you guys? I think it must be because it's my screen in here is kind of very, very slow in here. I don't know if it's my computer doing some updates or something, or hopefully there is no disruption like last times when we had the internet go away completely. Okay, same chemistry, but different physics because they have different masses. Yeah, okay. Sorry, Manuel. So isotopes. Manuel, is it just the writing on the screen, or is it even the voice is lagging?
The voice is good. It's just it lags a little when you
Uh,
write.
okay, yeah. So isotopes have same chemistry. Why is that? Because they have same protons. Okay, parentheses, same number of protons, not same protons. Okay, meaning also electrons when neutral. Okay, but different physics because they have different masses, namely the fact that they have different neutrons. That's different number of neutrons. Again, neutrons are the same everywhere in the universe, wherever you'll go and look for them. Okay, so that's the other point now we're going to raise for today's discussion. Probably we should expedite this thing a little. I don't know how far we are. We have we are way less than even the third of where we're supposed to be. Okay. So the atomic number of an element is the number of protons. That's always true. Okay. Or the number of electrons provided the atom is neutral. Okay. So both A and B. So the correct answer is C. A is correct. B is correct. So when you're reading a question and you have to be match the correct number of correct answers. So in this case, match the correct answer. What is the correct answer, I should say? You think A is correct, so you're going to circle A and move to the next question. But remember, in this case, it's looking for the correct answer, and both A and B are correct. Since you only have one choice, that you cannot choose A, you cannot choose B, because if you choose A, that selects B, and so on and so forth. The correct answer turned out to be C in here. In other words, when you're doing exams or taking quizzes like this one, you have to really be careful with the correct answer. Okay. I mean, you're right if you choose A, and that's why the questions now they have 2 points. If you end up choosing A in this situation, you're going to end up with 1 point out of 2 because you're right. Okay. But also, there is another point in here that is right too, which is B. And you cannot select A and B. So you have to select, in this case, C. So you get a partial credit in this situation. Okay, a nucleus with an atomic number of 44 and a mass number of 100 must have. So we have the atomic number 44. That's the number of protons. And the mass number, the atomic mass in here is 100. That means they have combination of protons and neutrons of 100. 44 of them, I know they are protons, so the difference must be the neutrons. So the correct answer must be 56, because if I add 56 to 44, I find 100. So that's basically how the math works in here. 56 plus, so that's basically how you need to really pay attention to this too, because that's going to be a lot of discussion later on. And when you're doing chemistry or when you're discussing with your students, especially if you're going to be teaching or something like that, it's very critical to use the correct terms, at least with them at this early age. Okay. So the periodic table is a listing of all known elements. That's one thing. It is not something to be memorized. Nobody does, but probably you will hardly find any chemist without it. Okay, at least he have it hanging in its probably office, in his classroom, in his probably bathroom. Everywhere you find you find him, he's got one with him. Okay, I may have exaggerated a little about the bathroom. So instead, we really have to know how to read it. Okay. So a chemist uses a periodic table, much like a writer uses a dictionary, in the sense that you're going to go and decipher things. It has a lot of information in it, as a matter of fact. So it's not just the order with which the elements are. So here is basically what the periodic table would look like. Again, you have the hydrogen in here on one side, you have the helium on the other corner. All of these gases, they're basically the so-called noble gases. They have their outer shells, they are filled. Okay, so they really don't interact with anything. They're inert. That's why they are also inert in terms of chemistry. And this elements in here, from lithium down, they are the basically metals, and in here you're going to be transition metals. Here is where the iron I was talking about earlier is. Okay, so if you count them, iron is what, the 26th element. Okay, the periodic table. Again, this number 26 in here tells me how many protons it has. Okay, how many electrons it has when it's completely neutral. Okay, and uh, helium, on the other hand, has two protons. When it's neutral, it has two electrons. When it's completely ionized, this is what I was talking about in terms of alpha particle. So if you read in the literature and they tell you an alpha particle, okay, especially in radioactivity and radioactive materials and things like that, that's what they mean with it. It's helium atom, but stripped of its electrons. It comes so energetic. It comes from the nuclear reactions usually, or radioactive materials, for example, polonium or something. I don't know. Polonium does. Yeah, I think it does. Produces alpha particle. That's what I think Rutherford used, and that's also what Marie Curie used to produce these particles. And they come from there and they are used, and then at the end they will find electrons and they will combine with them and they become helium again, which is an inert gas, doesn't do anything. Okay, makes your voice a little funny, but that's another thing. Okay, so lithium, beryllium, and then you go through basically the other elements, and then you have different elements. Some of them, like I said, are not found in nature. They're made in laboratories. Okay. By the time you find uranium, which is 92, where is uranium? 92 in here. 88. Here is uranium. It's okay. So that is where nuclear bombs were made of. There are two isotopes in there. Again, uranium 235. You have 235. Come on. I probably should change pens, or is it the... Okay. And it has 92 protons. So in this case, how many neutrons does it have? This is an isotope of uranium. Okay, this is not the most abundant one in nature. Okay, so it have 235. minus 92. So it has 143 143 neutrons. So you have more neutrons than protons to keep it together, to keep it from falling apart, actually. And even that, uranium 235 is not stable. Okay, uranium 238, though. Come on, just wanted to write to you. 92 and 238 has 146 neutrons, had more neutrons in it, 146 actually. And the extra three protons, three neutrons, I'm sorry, keeps it more stable than the 235. Actually, as a matter of fact, if you go to nature right now in a mine where they make uranium, most of it is going to be this isotope. Very tiny fraction will be this one. Okay, so what they do, they enrich it. They take it and they try to separate the two using physical properties. They separate them using physics actually to separate them, because chemistry, both of them have the same number of electrons. They both have the same chemistry. And once they are separated physically, then they take the one with the more 235 and becomes enriched uranium. Okay, it has more of the material that is used for bombs or for nuclear reactors or whatever you want to use it for. Okay, so then that is the more richer one. So both of them are isotopes. Both of them are similar, if you wish, when it comes to chemistry. Both of them have the same number of protons, but one of them has different neutrons in it. One of them has more neutrons in it, okay, than the other. So that's, and the heavier the atom, the more neutrons are actually needed to keep it from breaking apart. The more massive the atom, the more that you need from those, okay? So the periodic table is a highly organized table. Again, each vertical line is what I call the group, and each row is what we call a period. And this is how it looks like, okay? So here is your group. So group 1 through group 18, and then period 1 through 17. And this is actually need to be squeezed in here because 58, otherwise this line will extend and becomes kind of pyramid. And that's why you have to have it come more or less look like that way. So that's basically where these elements are. Like I said, a lot of these elements there don't exist in nature. So you really have to, I'm not a lot of elements, I'm saying this type in here, they don't exist in nature. So you have to, they were made in the laboratory later on. But again, this is one of their organizations. And usually it has to do with how many electrons there are in the outer shell. There is one for hydrogen, there is one for lithium, two are actually inside and one outside. So it's a total of 3. 11 for sodium, meaning that one outside, just like lithium and hydrogen, and 10 they're bound inside, they cannot do anything. So if in case sodium wants to do chemistry, it does it like lithium, it does, okay? Can afford only to give one electron at the end. The other 10 are tied together inside, just like the other 2 for lithium. Same thing with potassium. It has 19 electrons altogether outside, but only one of them can play whatever chemistry you want to do. The other 18, they're just like the other 10 from sodium, and so on and so forth. That's why this is group 1, because they can only give you one electron. Beryllium on the other side, manganese on the other side, calcium, strontium, and barium, and the rest of radon, they all have 2. They can give you 2 now, okay? And so on and so forth. All the way. This, guys, the 2, they're tied together. The helium technically cannot give anything for chemistry, okay? Same thing with neon, argon, krypton, xenon. All of this, they don't do that. They don't play any of those things. Okay, so that's in a nutshell how the organization in terms of the electrons. And now you have how many shells are actually in. This is the first one. This is the first and the second, and so on and so forth. So that's why 1, 2, 3. So the periods in here. So Mendeleev was very smart in putting it this way to help us get some ideas into the chemistry. How's going on in the year? What is this element versus that element versus the next one, which is completely different than this group. Okay, so that's how they are grouped together by Mendeleev. And it's a very useful presentation. Now, in terms of masses, it's kind of weird a little bit, okay? Because the fewer the electrons, the fewer the electrostatic forces between the shell and the nucleus. The more electrons and the more protons, the stronger this force. So the more attraction between them, and the atom starts to collapse on itself, and it's more dense because there are more of them in less space. So, for example, sodium versus argon, this line in here starts to decrease in size, okay? Because more and more protons are added to more and more electrons, making the electrostatic force look more and more. So when you look at the periodic table and you group from group 1 all the way to group 18, you're actually decreasing in masses. I mean, in size, physical size. I mean, not masses. Masses actually is increasing, but the physical size starts to shrink because of the stronger and stronger electrostatic force between the shell, the electronic shell, and the nucleus. Okay. In terms of chemical properties in general, they're grouped actually in the so-called, for example, noble gases. And then you have the alkalis, alkali metals, and the alkaline metals and transition metals. Iron is one of them. Copper is another. Okay. Gold is another. And they are all good conductors of heat and electricity. So these are the inner transition materials, and like the other ones which are transition, like I said in here. So these ones are squeezed in there. And now we have a lot of questions related to this one, and time is running out. So basically in here, which is larger, a lithium or fluorine? It's easy this way, okay? The lithium, of course, is, okay? Because it has less protons and less electrons versus the fluorine, okay? So again, we talked about the model and the fact that there is a physical model like the solar system that replica. And then you have the conceptual model. Conceptual model describes a system based usually on its properties, the properties that you have in mind, okay? And I said already that it's a good idea to make it with a conceptual model to give you an idea of what properties you're trying to describe. I already mentioned the fact that spectroscopy is a property of material. When you heat up an element, for example, take a spoon and put it under fire and protect your hand. Don't put it right on your hand, okay? At some point, it's going to be so hot that it starts to glow. If you take a prism, for example, and break the light from that is coming from the source, you're going to see certain frequencies depending on what's the spoon is made up of. So you really have to excite the atom first. You have to get it to get some energy first and then see what it gives off. Okay. When it gives off, that's actually an emission spectrum. So that's the process with which trying to get things, how to analyze objects. Okay. So an atomic is a fingerprint, a signature. For each atom has its own signature. Again, historically, it was discovered in that that's elements have specific spectral lines. And then John Balmer basically was the first one to put it in a model, mathematical model, and he just basically followed the data, and he found that they follow this model. It was later on explained using quantum mechanics and different new branch of physics that they basically developed from there. Okay. So strontium, for example, this is its spectrum line. It's not just one line, okay? All of these lines together. Some of them are towards the violet, the blue. Actually, I don't know if you see this line or not, but there is a line all the way to the line to the end of the spectrum. So if you have the PowerPoint, probably you can look at it. I don't know how it comes out on the screen. And then it's going to shift toward the blue, and now more toward the green, now toward the yellow, some lines in the yellow, and then the red. And even the red, there are different shades of red, different hues of red, all the way to the dark red. And then after that, we can see. This is our visual looking. Same thing with potassium, barium, and copper in here. And you see these lines, for example, two yellow, then followed by four, what looks like a green, different shade of green and cyan. Then this is actually more cyan than anything, or this are blue, and then shifted toward. And you count them, and you do an experiment later on for a specific structure that you don't know what it's made up of, and you find these lines specifically in this order, in this values, because each one of them has a specific value in here in terms of either wavelength or frequency, then you know that copper is present. Okay. It has to do with the energy levels, actually. When you excite an atom, it gains an energy, and the electron jumps from an energy level to a different energy level. But the atom wants to go back to its ground state, to where it was before. So what it does is it releases that energy, and that is what we discover. What we will discover in there. This, because the energy level are specific for the atom, the transitions are also specific for the atom, and the frequencies, they are proportional to the jump in energy. So the jump is unique to each atom, the frequencies are also going to be unique, and now we know that that atom is exact. Now, sometimes it makes only a single jump, so we'll have one frequency, and sometimes it makes several jumps before it reaches the ground state. So we'll have different frequencies in there that we can see. In other words, question is, how come hydrogen atom has a single lousy electron at the end and makes up this many lines? Well, because that same electron can make different jumps before it reaches its ground state. It's not like I have many electrons coming and making those different jumps. It's only one that was excited so high in the energy level, and then now it wants to come back to its ground state. It makes this jump, and the bigger the jump, the higher the frequency, the more the frequency is toward the violet, the smaller the jump, the smaller the frequency, the lower the wavelength, and the more it's toward the red. So that's basically how it is in a nutshell, basically, the entire rest of the discussion, if you wish. So each spectral line is an atomic spectrum, specific frequency of light emitted by an element, okay? So each jump is specific to that atom. The hydrogen spectrum consists of many spectral lines. How can this element have so many lines? It's only one electron can be boosted to too many different energy levels, that's all, okay? So it's not like I have a bunch of them, or different atoms jumping at different levels. No, it's only the same electron going into different energy levels, that's all. When an atom is excited, its electrons are boosted to higher energy levels. That's basically what it is. C is kind of amusing. Okay, this slide and the next one, ignore them. I have no idea what they're talking about. Doesn't make sense, okay? The frequencies of light emitted by an atom often add up to a higher frequency. So it doesn't make sense, okay? The frequencies don't add up. They are discrete numbers, okay? So maybe what is meant with it is that there is one jump, another jump, and another jump, okay? But they don't add up to a higher frequency. They add up to a spectrum. So, okay, Max Planck, German physicist, hypothesized that warm bodies emit radiations in discrete bundles called quanta. Energy in each never. So basically, he discovered, he was the one who basically had that famous constant that later on was named after him, and that is the how much every transition basically is proportional to. So this number is a constant. This is similar to the speed of light, 300,000 kilometers per second. This is similar to the value G for gravitation, okay, which is 6.67 times 10 to the negative 11, which is uniquely define our universe in the sense that had this number G was bigger, all the objects in the universe would have stuck to themselves a long time ago, and we would not have a chance to be here sitting and talking about them. And if G has been any less number than that, we would not be here also to talk about them, because everything would have sprung apart. Well, this number H also is how much the energy levels are transition from energy level to energy level. And this number is 10 to the negative 34, actually. It's 6.6 something times 10 to the negative 34. And the units for it are actually joules and seconds. Okay, it's like a power, actually. Joules over second. Oh, no, joules times second, I'm sorry. Okay. Uh, did I make a mistake? I think I did. Okay, forget about the units. For right now, the number is 10 to the negative 34. And this number, had it been any smaller than this, again, the physics that we have known in here, the entire universe would be completely different and we would not know it at all. Actually, the atoms will be completely basically the transition between will be continuous. Had it been any bigger, and then we would experience quantum effects. We will be actually, then you can be in two places at the same time, which is good. Then you can be sleeping and working at the same time, sleeping and probably at the bank at the same time, and then you can go through walls and you don't have to need doors and things. There are all kinds of weird quantum effects that would experience at that point. Okay, so again, these are some of the constants that they govern the universe: the speed of light, the constant g that we have seen, and now another constant, Max Planck's constant h. Okay, Einstein also was able to come up with the same notion that actually the energy levels are quantized, and this is actually what Einstein won the Nobel Prize for. It's not relativity, okay? When trying to explain the photoelectric effect. As a matter of fact, the energy of light itself, that's how basically Einstein explained that light is made up of particles, and those particles hit the electrons inside the substance, emitting them, and that's how electricity is produced in the photoelectric cells. And that's probably some of you also what you guys are using on your roofs and to generate power using the solar power. That is actually the photoelectric effect that Mr. Einstein discovered. This is how this relationship, I mean, this squiggly line in here means it's proportional. The energy of light is proportional to Earth's frequency, meaning that the violet light is more energetic than the red light, which is more energetic than the infrared red light, which is more energetic than radio waves, which is more energetic than even longer wavelength. Now, the violet is less energetic than ultraviolet, less energetic than the X-ray, less energetic than the gamma rays, which are the highest energies that you can think of because they have the highest frequencies. So energy and frequency, they are proportional to one another, and their proportionality is exactly that number h that I gave you. Yeah, so the unit that I said before is correct. Okay, h is joules times second, because this makes sense. Energy is in joules, h is in its own units, and frequency is in units of 1/second, if you put it there. So actually, this is the constant that I was talking about. Okay, so it's proportional to it. Is it hf or is it h bar f? Doesn't matter. Okay, h and h bar, there is another constant also that comes in mind in here. We're talking about this one, which is just h divided by 6.24, 6.28, I'm sorry. Okay, so in the relationship, E is proportional, exactly equal to H times F. The symbol F stands for the frequency emitted by light, and E stands for the energy of the photons, its own energy, okay? So how much energy it has, okay? So the more frequency, the more energy. So when you look at the spectrum for light, for the electromagnetic spectrum, that is actually the spectrum also for the energies too. I think we're running out of time, so we probably need to get into some questions in here. Which of this has the greatest energy per photon? Of course, red light has energy, but green light has more energy than it because it has a higher frequency. But blue light has even more energy than the green light because it has more frequency. Again, so when you look at the frequency, you're looking at the energy also. That's why actually it's not a good idea to be exposed too long for X-rays, because they have actually more energy than the blue light or the violet light or even the ultraviolet light. Gamma rays, they will do even more damage. So it's not a good idea to be exposed to them for a long time, because they can actually go inside your nucleus and start messing around with it, because they are very short wavelength, extremely high energetic, a lot of energy. Again, which has the smallest energy in this case? You have infrared, visible light, and ultraviolet. Again, ultraviolet is more energy than light because it's more than violet, and violet is inside the visible region. And visible has more energy than the red. I mean, the red is actually toward the lower end of the energy when it comes to visible light. Infrared is less than that, so it has less energy. So the correct answer is infrared. So Niels Bohr actually came up with a model to explain again the stability of the atom, and he had this wave formations. Basically, that's how the wave idea started from. Okay, and using the Max Planck constant and using the quantization of basically light and that of the electrons also, he was able to come up with an energy levels to explain, among other thing, Balmer's basically spectral lines, and it came up with an exact mathematically matched perfectly. Okay, the problem with it is that his model was not initially correct because of the fact that it would lead to the fact that the atom would not be stable because the atom would collapse on its nucleus. And even in the best approach that he came up with later on, and you will see the experiment in here, and he had to introduce this n, which is an integer, okay, for the energy levels, and that the energy levels are discrete. And he came up with a beautiful model. Again, it's just a model. This is just an initial model which explains experiments, okay? Of course, if it later fails, you have to come up with a different physics, and it's exactly what happened in this case, because that's when the need for quantum mechanics came about later on. So, in here, which of this is a quantum number? Of course, it has to be an integer. 1 is an integer, 2 is an integer, 3 is an integer, 7 is an integer, but 0.02 is not an integer. That's a decimal point. So the correct answer in here, quantum numbers are of the form 2, 3, and so on and so forth. Okay, they can be positive or negative, which keep them integers. Okay, but for the energy levels, they actually have to be positive integers. They are 1, 2, and so on and so forth. They cannot be 0, though. There is no energy because actually, according to Mr. Palmer, the energy levels are separated by 1 over n squared. Okay, when n is the integer that we're talking about. Okay, and n can be 1, 2, and so on and so forth. Okay, all the way to infinity, if you like. And at that point, we have reached, actually, we escaped the atom. The electron has been extracted, actually. So Bohr explains why atoms don't collapse. Electrons can lose only specific amounts of energy. So in this case, that explains that. But there was another problem actually with the model itself, namely that actually every moving charged particle will radiate energy. So it needed to explain that part too. Okay. So ground state is when everything sits and does not go any further. So planetary model of the photons are emitted by the electrons move around the energy level. The energy of an atom is equal to the difference so between two different levels. So that's the emitted frequencies. Again, all of these are models and representations of the real thing. And this is basically n equals to 1, 2, and 3, and everything else. So that is basically the different energy levels that the atoms will, I mean, the electrons can occupy. And in addition to the energy levels, there is another thing called the orbital motion, which is the number L, which is also another integer. In addition to that, there is the spin also. That's why we're coming to a shell model, and the shell model takes all of these quantum numbers into account, okay? So this is actually an experiment that we can see the way that he was basically the only reason that the electron can exist in specific energy levels if the wave function becomes a standing wave basically and wraps around it at least with n equals to 1. With n equals to 2, you have two wavelengths wrapping, and they have to match from the beginning to the end in order to have a standing waves. For n equals to 3, you have three wavelengths, and that is standing waves that form for his model in there. And now the shell structure is more actually a representation of how that is. So the first shell is 2. The second shell will be 8. 2 plus 8, so you have possibility of 10 electrons. And the second shell, the third shell is 2 plus 8, which is 20. No, sorry, 18. And so on and so forth. So basically that's how, yeah, 16 plus 2 is 18, and so on and so forth. So this is how the shell representation, again, using these models. You have up to 2 for the first shell. They have one electron, two electrons. The second shell, again, now you have In addition to the two on the lower one, you have one, you have two, you have three, you have four. Now allowing for the spin now, you have actually one together where they have two opposite spins. There is a principle in here that dictates that they cannot have every single number the same. They cannot have the energy level n equal to the same. They cannot have the same. I mean, if they do have the same number n, that's fine. Then they cannot have the same orbital number l. And if they have the same number orbital l, at the end, the spin cannot be the same. So at the end, you cannot have everything in here, all of them match. So if they have the same n, they may have the same l, but they cannot have the same spin at the end. So these electrons, they have the same n, they are in the same energy level. They can have the same orbital number. They are in the same orbit, basically. And now, if one of them is spinning up, the other one is spinning down, so that now they can coexist. Okay. Now they are actually, they cancel one another, just like the helium in here. You have two electrons. They are on the same energy level. They are on the same orbital number. Okay. But at the end, they cannot be spinning in the same direction. Now they are going to exclude. They are going to mutually exclude one another if that happens. So what they do in this case, they lock themselves in the opposite spins, and now they can exist in that energy level with that same orbital number. So that's basically what the model in here for the shell structure is. So at the end, all of the levels are saturated. All of the energy levels, that is, are saturated. They're full because they have all the electrons existing on the same energy levels with the same orbital numbers with opposing spins, and now they cannot do anything. That's why this noble gases are inert, because these electrons, they're locked now every which way you can think of. Now this electron in here and that outer electron in here and that outer electron in here, they're free to participate in any chemistry you wish. So this is, if you wish, the shell model explains a lot better the 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 uh, the the periodic table. Okay. So we have a couple of questions for today. You have the quiz, not the quiz. I'm sorry. You have the review that is online. Hopefully, you guys can go and finish it. And I know only a couple of people so far have done it, so I hope that everybody else will take advantage of it. And also, you have the exam. Any questions before I stop recording?
How many questions were there for this
Exam.
lesson?
For this, two.
Two. Okay. Thank you.
Okay. And for the exam, there are 55. So I'll see you guys Thursday morning. I think I hear that the weather is going to be better. So hopefully, we'll have a much better weather then. See you guys.
Take care.
You too. Bye.